Right, this is going to be a review going back a little bit farther than the beginning of the semester, but in context of laying into the pictures and the units and the like, touch on, touch off, with regard to materials and how in fact we make use of relationships between things like force and area and distance to come up with some basic mathematical graphs which lead us to concepts of slope and area underneath these graphs to describe how materials behave. So let's start with the context of, at the very base, knowing that in the unit circle we have this concept of pi over 12, pi over 6, and pi over 4. And realize that along with 0, which has coordinates of 1 and 0, we have the 15 degrees, which has coordinates of 0.2588, sorry, 0.9659 and 0.2588. That one, of course, was the memory one. These other two, of course, having coordinates of 0.866 and 0.5, and then here coordinates 0.707 and 0.707. Remembering, of course, these are the square root of 2 over 2. This is the square root of 3 over 2. This is 1/2, and these are just numbers that come from the sine of a small angle is the small angle, more or less. And the cosine of the small angle is the small angle minus 1 minus the small angle squared. So this was this concept of the unit circle. Remembering it had a radius of it had an angle of 2 pi, a circumference of 2 pi feet, an area of pi square feet, a volume, if you revolved it, of 4/3 pi r cubed, which would be feet to the cube, and then a moment of inertia, second moment of the area of 1 pi over 4 times feet to the 4th. So we kind of get a lot of concepts out of this, and the fact that we know that the cosine of 75 degrees is the sine of 15 degrees, and the fact that this basic 45-degree slice just keeps on flipping and flipping around. So winnowing ourselves down from, of course, the 1, 2, 3, 1, 2, 3 over 2, square root concept that you all have mastered at this point. Remembering that we measure our angles from the standard position angle this way when we are dealing in a right-hand coordinate system, and usually in survey from north being 0 and a positive right turn angle. So that was the unit circle. A lot there, lots of facts and lots you can come from that. Next one, of course, was the circle of units, and we'll just talk with the concepts here going around, starting that specific gravity on one leg and unit weight on the other, and of course force up on top. Along with specific gravity in the unitless category is angular displacement, which is radians. Then we have distance, we have area, we have volume, and we have mass. From force we go to work, which is F dot D. We have power, which is work over time. We have pressure, which is force over area, or work or energy over volume. We have torque, which is R cross F, and then we have mass density. Remembering that 1, 2, 3, 4, 5, 6, 7 to the top, and then 8, 9, 10, 11, 12, 13 going around. We have then specific gravity unitless, angular displacement unitless, feet, square feet, cubic feet, slugs, pounds, foot-pounds, foot-pounds per second, pounds per square foot, pound-feet, slugs per cubic foot, and pounds per cubic foot on the English side, if you would, or the imperial. We have unitless, meters, square meters, cubic meters, kilograms, newtons, joules, watts, pascals, which is newtons per square meter, or joules per cubic meter, Newton meters, or meter newtons, not joules, because this in fact is torque. We have kilograms per cubic meter, and we have newtons per cubic meter. We remember that the density of water is 1 gram per milliliter, it is 1 kilogram per liter, and it is 1,000 kilograms per cubic meter. We remember all those things, and we also remember that it is 62.4 pounds per cubic foot, which is a little bit less than 2 slugs per cubic foot. We then want to remember that there are 3.781 liters equals 1 typical U.S. gallon. So in that we have a real good sound basis to start talking about things when we graph one thing versus the other. So we'll move on to that with a new slide, which is going to be a blank slide, and we'll see how this continues. So from here we had some pictures, and the first picture I think we had came along this way, and it is then testable in so much as we know that we have basically soil comprised of solids and voids, and the voids are comprised of water and air. Okay, and we know 2 base definitions, and that is in fact moisture content equals the weight of the water over the weight of the solids, and void ratio equals the volume of the voids over the volume of the solids. We have a lot more that comes from that, but at very base, one other major formula was that the dry unit weight is equal to the moist unit weight over 1 plus the moisture content, when moisture content is expressed, of course, in a decimal, with 10% being 0.1. So soil weight volume chart was a picture. Lots comes from that. Sliding now into the concept of compaction curves, which in fact is the concept of Proctor. Proctor was graphed on moisture content on that axis and unit weight on the other, with something out here called the zero air curve, and a set of compaction curves with increasing amounts of energy per volume, where you had the optimum moisture content being that moisture content which got you the maximum dry density, right, along there, called the Proctor density. And typically we are looking both at a modified Proctor and a Proctor density, with the modified Proctor being a tougher standard, and this modified Proctor or Proctor, bigger hammer, more blows for compaction curves. So that concept. Still going back or forward, we had another graph in terms of grain distribution size, a soil grain distribution size or an aggregate grain distribution size. It was percent passing versus diameter on a log scale. And so we'll have a curve that looks either something like that or like that, depending on which way your coordinates go. There's numbers that describe this curve, but something with a long shape is well graded, lots of different sizes. Something with a sharp shape has more sizes of one particular, in other words, something like this has a lot of one size shape. So this was a gradation curve. So we're now talking about curves where percent passing or diameter you realize that these things have units. So in this case, moisture content unitless, dry unit weight has units of weight over volume. Moving on to the rest of the shapes and some of the concepts, we'll go to Home, Insert, New Slide, Blank, and let's think about, as we start pressing on things, first to the device and the concept of Hooke's law. Hooke's law would say that, in fact, if I have a spring, I'm going to have a change in x, or a length change in x in the spring, and a force is going to be directly proportional. The bigger the change in x, the more the force. Change in x has units of distance. Force has units of, in fact, force. Pounds per inch, newtons per meter, or newtons per millimeter. We then have to realize that the value of the function in this case is force. The slope, which is called the spring constant K, is force over distance, and the value of the area is force times distance, or essentially the amount of energy stored in the spring. There's an analogy then when we get into the classic stress-strain curve, where along the x-axis we have strain, which is change in length over length, and over here we have stress, which is force over area. Once again, in this case, we're looking at a material generally that's going to have some, hopefully, some sense that you have a linear relationship. I'm trying to pull that out here now. You have a linear relationship. Notice I'll get that back. I'm going to go back down to here. You have a linear relationship to a point that's called the elastic, right, or the proportional zone, where effectively if you add more stress, you have strain, and then you go back and forth along this line. Eventually you get to a yield point where you have yield, or on some materials, or fracture on others, where a small increase in stress leads to a large increase in strain. Something stretches, and then eventually you go to a point of ultimate failure, where in this case we have what's called the yield stress here and the ultimate stress there. Yield strength or ultimate strength, yield stress or ultimate stress, and that has units of force over area. This curve, what is most important about the stress-strain curve, besides the fact that you can solve it out for a formula that please do not forget, is that the modulus of elasticity, or Young's modulus here, has units of stress. In other words, the slope has units of the y, or the ordinate axis, divided by the x, or the abscissa axis, but this is unitless, so this has units of stress, with steel being in the order of 30 times 10 to the 6th psi, or 30 times 10 to the 3rd ksi, kips per square inch, where psi is pounds per square inch and ksi is kips per square inch. This, in fact, leads to eventually this formula that looks like this. The change in length is equal to the force on something times the length divided by its cross-sectional area divided by its modulus of elasticity. That comes from this graph, and the units in fact do work out. So remembering the concept of Hooke's law, which can also exhibit itself not just in a spring but in any solid, and this idea of stress strain, with in fact knowledge that most steel has the same modulus of elasticity, but many concretes are going to vary based on the strength. But most importantly, realize that the value, in other words the strength, the stiffness, and something called the toughness, which is the area underneath this curve, all have the same units of stress. So that curve is a large manifestation of that curve speaks to a lot of engineering, especially when you start trying to keep things down here in this zone so they bounce back to where they started. If in fact you do take something beyond this yield point, the material generally will rebound in a line parallel to the elastic, and you have something called residual strain. Alright, so this then finally left and led to the concept of, go to a new sheet, of the fact that we don't always look at our stresses as unidirectional, but we look at it like we do in lots of things by dividing our stresses into two components, which we usually call normal or axial and shear. And so the concept, as we go now once again to pens, that we are going to, if we're going to do a Mohrs circle or a discussion of combined stresses, on one axis of our graph we put the axial stress or the normal stress, and the other one we put the shear, so axial or normal, and on this one we put shear stress. Remembering that we make this assumption that in fact tension is positive and a counterclockwise spin is positive. So tension is positive in both cases, along the axial stress, and counterclockwise is positive. And what we end up doing then is realizing that these are also PSI or KSI, and this is also PSI and KSI. And by effectively taking a soil or a piece of concrete and realize that it is under different stresses, perhaps in this direction and in that direction, we can graph up the stresses on face 1 being the vertical and face 2 being the horizontal. In this case, if there was no shear, we have tension on face 1. We might have a tension someplace like that. And when we have compression, which is negative on the other face, right, we can then draw a circle, bad as it is, and the point on that, any point on that circle is going to describe a combination of stresses in the axial or normal and in the shear or basically perpendicular to the normal set of faces. So while this may exhibit itself like this and like this and like this and like this, when you go ahead and did that at some degree here, you would have some shear going across, and in this case the shear would be positive on one face, on face 1 positive, which would be this way, and negative on the other way. So that what you most want to grab is that you graph two types of stress with the same units on this, what is called Mohrs circle of combined stresses. So these concept that graphs, moving on to the last and probably most important concept to get out of all of these, is this: that anytime you have a graph graphing one thing versus the other, and we'll stick with two-dimensional graphs at this point, that you have to realize that the concept of the value has units, which you just read out the value. I'll use the example here of perhaps linear load. Linear load would be pounds per foot, and this would be feet. So the value in this of this function would be pounds per foot. The derivative, or aka slope, is going to be change in y over change in x, and you have to get pretty good at going pounds per foot divided by feet. And if you thought about that, that would be fines per foot divided by feet would be pounds per foot squared. But the integral, which would be the area, AK area, will have units of pounds per foot times feet over 1 or units of pounds. So grasping the concepts of value of the function, derivative and integral, and the fact that you get the units of the value by just reading the y-axis units, you get the units of the slope or the derivative by actually solving out some dimensional analysis of the units of the y divided by the units of the x, and remember how to divide fractions. It's important that you grab these skills from college math or algebra, learn how to divide the fractions and divide the fraction units as well. And finally, the concept of integral, being the area underneath is one set of units times the other. We remember the special case of stress versus strain, where they all turn out to be the same. Confusing or not, that then is the review for the most part with regard to the semester's class, and to grab these last two concepts, which are important enough to cover over and over and over again. We'll finally end with that, and that is in fact that work is F dot D, or the dot product of the force and the distance, and torque is R cross F, but then also realizing that work is also called a dot product or a projection calculation. It is also equal to the magnitude of the force, or the magnitude of one vector times the magnitude of the other direct vector times the cosine of the angle between them, whereas torque is the magnitude of one vector times the magnitude of the other vector times the sine of the angle in between them. Because as we remember, the calculations for either work or torque being I, J, K, if we go with force in the x, force in the y, and force in the z, and distance in the x, distance in the y, distance in the z, remember we cross those out, multiply each of these together, and get a scalar quantity. It allows us to then solve for the cosine quite nicely. And again, remembering in R cross F, which is torque, I, J, K, R in the X, R in the Y, R in the Z, F in the X, F in the Y, F in the Z, across, 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 these, minus these. This is a vector product. But as well, you can use that same calculation to do, amongst other things, the normal of a plane defined by 3 points. So, remembering that we can do it in our calculators, we can do it in Ruby, and we can do it in Wolfram Alpha. Or do it by hand, or do it by projection for the dot product, or area for the cross product, all empowers us to go eventually back to, going all the way back to the top here, go back to there, lets us go back to this chart and start to realize that things like work is more than just units. It is F dot D, and pressure, or I'm sorry, torque is R cross F. Eventually you will see that we've talked a little bit about the fact that for the concept of time in the middle, you can go with not necessarily distance, but the concept of angular deflection, right, being the same as distance, angular velocity being the same as velocity in terms of a rotational world, and angular acceleration being the same as acceleration, in terms of mass being the same as the real moment of the area, in terms of momentum, which is mass times velocity, or P being the same as angular momentum, knowing that kinetic energy is 1/2 mv squared, but it is also 1/2 the moment of inertia times omega squared. Remembering that F equals ma, but also that torque equals I alpha. So there is going to be a direct relationship between the rotational world that we're starting to see in Mohrs Circle when we start talking about shear versus axial stresses and everything else. So that is a 25-minute review. I will post this and take comments. You should be able to pull and make up your own kind of sheets for this, which I will talk about allowing if they are handcrafted and your own and they fit inside your calculator case. I will also allow and encourage you to put some of this information in a format that stays in your calculator as we then move on to the concepts in concrete, which we began speaking of last week. Thanks for listening. And send your comments, please.